Okay, welcome everybody. So far for this big chapter, we've done both the stoichiometry, solution stoichiometry, and now really the last part of this quantitative section of chemistry, for now at least, is going to be gas laws. And they all kind of go together. I'm going to talk to you about what it means to be a gas, how gases behave, and then all the math that goes with it. Now, some of this may seem familiar to you. You should have seen pretty much all of this last year in honors chemistry. I feel like it was important for us to really give you a full picture of how gases behave, what the gas laws are, and so on. So, what does it mean to be a gas? Well, here I list all of the important features of what it means to be a gas. And the first thing is that the gas volume, it's going to change a lot with pressure changes. And so this means that you can compress a gas. And if we were to draw a gas in a box here, so here would be my box, and I were to zoom in and draw my gas particles, my gas particle would be like this. So these would show my different gas particles inside this box. And so it makes sense that, there's going to be huge changes in volume when I change the pressure. And this is because there's lots of space between the gas particles. So in a gas sample, we have mostly empty space. I can demonstrate this for you with a syringe and show you how gases can be easily compressed. The other thing that gases will do is they're going to change a lot with temperature. So, the volume will change as you change the temperature, and I'll show you a graph of this on the next few slides. Heating is going to increase the volume, cooling is going to decrease the volume. The next thing that's really important is that gases have pretty low viscosity. That's meaning that they flow easily. Certain liquids are really viscous, like molasses is an extremely viscous liquid. Whereas gases, those, you don't even notice them flowing because they move easily. They can leak through small pinholes, they can spread out of their own accord, and these processes are called diffusion if you're leaking through a pinhole, or as we'll talk about later, diffusion if you're just spreading out without any help. The density of gases, now because of their large spaces between the particles, they have very low densities, and we measure them in grams per liter. And if you think about this, if we had a liquid would have a density of grams per milliliter. So what that's telling us is that the gases are 1,000 times less dense. So they're 1,000 times less dense than you would get if you had a liquid. And gases are miscible. And this is going to become very, very important when we talk about partial pressures. The gases will usually completely mix together. They spread out, they diffuse, they completely mix. So if I were to take, and show you a box and now put two gases in there, so now I have my one gas, and if we show our second gas will spread out as well, and you'll get both gases. Notice how I'm drawing the gas particles, and this I'm going to come back to again when we talk a little bit more about kinetic molecular theory in the next video, but notice I draw the gases, the particles, as pinpoints. And that's because, as I'll say this again later on, gases, they have no molecular volume. And also, they have no attractions. And they're separated by large spaces. So there's large space between the particles. Now, something that gases do is exert pressure. All gases exert pressure. When I think about, what is pressure? Well, it's a force over an area. So my pressure would be equal to a force over an area. Now, since we have three-dimensional shapes and three-dimensional containers, the pressure and the volume, as you can see here, are inversely related. So if I start increasing the volume, I will decrease the pressure. So as the area goes up, or the volume goes up, the pressure will go down. As the force goes up, which is mainly due to temperature, then the pressure will go up. So these units of pressure, how do I measure it? It should look familiar to you. We did these all last year. So we have atmospheres, we have millimeters of mercury, or torr, they're the same thing. We have pounds per square inch, and we have a pascal, which we'll always use kilopascals because it's a larger unit. And so we can convert between these different units if we look down here, STP, which you're pretty familiar with, if I have 1 atmosphere, I have 760 torr, which is also 760 millimeters of mercury, and it's 101.3 kPa, and in pounds per square inch, it's 14.7 psi, pounds per square inch. Now at STP, at the standard temperature, 273 Kelvin, and this 1 atmosphere of pressure, gases will automatically occupy, if they are acting ideally, they will occupy the same volume called a molar volume. And this molar volume is 22.4 liters per 1 mole. And so when we were doing mole calculations and I was asking you how many liters of a gas is this, if I gave you a certain number of moles, like 2 moles, you knew to multiply 2 by 22.4. And this is called molar volume. All gases, because they occupy the space that they're put in, and because they behave as tiny pinpoints, they will take up the same volume. This is true for any gas that will be behaving ideally, and we'll talk about what it means to behave ideally in a little bit, or on the next video actually. So how do you measure pressure? Well, 2 ways. We could use a barometer or we could use a manometer. Now the barometer, it's going to measure atmospheric pressure, the pressure outside. The manometer, that's a device that's going to measure pressure of a gas in an experiment. And what I think is really interesting that people don't realize that, here on Long Island, for example, we have about 1 atmosphere of pressure constantly pressing upon us. And we sort of take this for granted. But when I look at, the effects of atmospheric pressure on a system, I can see that the pressure actually is really quite great. And what these people did, and I'll demonstrate this in class with Crush the Can on a smaller scale, but you can see that pressure can even act on a large scale here. This tanker was intact the day before they took this picture. They sealed off the container, and it had gas inside it, just regular air inside it. And they sealed it off when it was hot. And overnight, as the gas cooled, remember, as temperature went down, the gas exerted less force until the pressure went down. Meanwhile, this is inside the tank. But if I look outside the tank, the pressure remained constant, as atmospheric pressure relatively will. And so what happened was the pressure outside became greater than the pressure inside. Enough so that this got completely crushed. So I'll do something with, this happened slowly over time, but I'll do something quickly in class with you to show you the effect of outside pressure. Now, what does a barometer versus a manometer look like? Well, on the left here, I have a barometer. And, nobody's carrying around open containers of mercury anymore, but this is the essence of how a barometer is working. The atmospheric pressure is pushing down on a pool of mercury. And that causes the mercury to rise up this tube. How much this mercury rises up the tube is the height, and that height is equal to the atmospheric pressure. Again, standard pressure is about 760 torr, or millimeters of mercury, hence why they call it millimeters of mercury. Now what happens if I actually have something like a manometer here? So with this manometer here, I have a gas inside this container. And I have an open end on the other side of the container. So now what's going to happen here is the pressure outside is pushing down. The pressure of the gas is pushing this way. They're opposing each other. Who's winning here? Well, if you said that the gas is winning, that's good because the gas is what's winning. The gas is pushing down more than the outside pressure. Well, how much is the gas pushing down? Well, the gas is pushing against the whole atmosphere. So the pressure of the gas is equal to whatever the atmosphere is pushing plus the difference in the height. And so this is a common question that you'll see on SAT 2, you'll see this on AP, you'll see this in IB. I want you to know about these devices, a manometer versus a barometer. We'll talk more about barometric pressure when we start, measuring gas pressures over water and how the barometer becomes really important. So what's our goal here in this part of the chapter? Well, it's to understand, how gases behave, but it's also to be able to mathematically manipulate them. And so these laws here, the first set, are what I call kind of like the combined gas laws. You can combine all these together and you will get what's known as the combined gas law, PV over T in one condition equal to P2V2 over T2 in the second condition. The first set of this law focuses on the pressure and the volume, and you keep temperature constant. So temperature is not affected. And what happens is if you graph this, if we have pressure versus volume, we get a curve like this. And I would definitely know this curve. I would know the name is Boyle's law if you forgot it, and I would know that P times V is equal to P times V. You can use any units you want for pressure or volume as long as you keep it constant. And when we do the practice problems in a little bit, you'll see what that's like. Now, what if I keep pressure constant? Well, in my next law here, that's exactly what I'm going to do. I'm going to hold pressure constant, and I'm going to look at volume versus temperature. In this case, when I graph volume versus temperature, I'm going to get a direct relationship like this. I always remember divide, like I'm doing here, direct. Something that's really important is that you have to use Kelvin temperature, like really, you cannot use Celsius. It will get you the wrong answer. It has to be the absolute temperature scale of Kelvin. Remember that Kelvin equals degrees Celsius plus 273, so you can just convert it easily like that. Now, what if we're talking about, looking at the number of moles? If I'm looking at the number of moles, well, then I would use something called Avogadro's law. And that looks at, well, as I increase the moles of a gas, the volume will go up. 1 mole would be 22.4 liters at STP. 2 moles is 44.8 liters at STP. So you can go through and you can see if I increase the moles, I increase the volume. I can even pull in Avogadro's law here, and I can relate P versus V over NT. And I can relate that to a second condition. And what's interesting about this is that if I plug in real numbers here, and I'll do that right here before we talk about the Charles law gas, if I put in a pressure of 1 atmosphere, so I do STP, if I do 22.4 liters, if I do 1 mole, because that's how much 22.4 liters, and we're at STP, so 273 Kelvin. If I put these numbers in, I'll always get the same value, 0.0821. And this should look familiar. This is the gas constant. Atmospheres, liters, moles, Kelvin. And when we do the ideal gas law in a few slides from now, you'll see like, oh yeah, that's what R is for this particular unit. If you change atmospheres to torr, you change atmospheres to kPa, well then guess what, that R value, that constant is going to change. Now what does volume versus temperature look like? Well, here's, sort of a mock graph of this from our textbook, the AP textbook. And so, you could plot points here along here, volume versus temperature. And they're actually doing it in Celsius. I wish they did it in Kelvin, but they didn't. And they do this in volume for centimeters cubed, milliliters. And then they extrapolate the graph back to the origin. And what they see is that when you extrapolate the graph back, you get to this temperature, this minus 273, which is absolute 0 Kelvin. And once you get back to 0 Kelvin, interestingly, the gas sort of stops moving, the particles. At that point, you're really no longer a gas. You've condensed into this sort of, new phase of matter. And it has a name, it's called the Bose-Einstein Equilibrium. And also, interestingly, we have never actually reached 0 Kelvin. In the lab, we've gotten really close. I believe the number is about 1/1000th of a degree Kelvin. Close enough, I would say. But we haven't actually reached 0 Kelvin. So what we'll play around with tomorrow is this, let's see the gas laws in action with a web animation. And it doesn't work on the iPad. We have to do it on a computer. Hopefully our computer in our room will actually load this and we won't have some Java mess on our hands. But this shows you, like what happens. If you want to try this at home, here's the web link down here. And this kind of goes through. And what they do is, and what I like about it is you can manipulate the pressure. You can manipulate the volume by moving the piston. you can manipulate the moles of different gases, and you can manipulate the temperature, and you can set stuff constant. And what they do is you can look at the velocities of the gas particles, and what I love about this is that they highlight one gas particle and makes it really easy to keep track of. And so when we talk about temperature, and we'll do this, quite a bit when we talk about temperature, equaling average kinetic energy, which is related to velocity, you get to see that. You get to see that, where's the average velocity, where's the average speed and the average energy of this. And so when you keep an eye on the red particle, you'll see it get slow, you'll see it get fast, you'll see it move in the middle, and then they actually are nice enough to graph the average for you. And we could even make sort of like a curve over this where we have like this, like, a bell curve, where most of the particles are sitting right here at the top. Very few particles are down here, even fewer are up here. They're sort of all over the place. We'll come back to this graph again. I know I keep saying we'll come back to stuff because there are actual dedicated slides to this idea. So now, so far what we have is this PV over T equals PV over T. Notice I leave out the N, the moles, if you were wondering. And I do that because generally the moles will stay constant. If we change the moles, we could put that in. I can do that in a different color here, like green. We could put in our N1 and our N2, and then we could change everything up. And like I said, like when we take PV over NT, we get a constant R, which is 0.0821, and the units for that are atmospheres, liters, moles, Kelvin. And this is our constant. This is taking PV equals nRT, a gas law that you learned in honors chemistry, and rearranging it. But just to go through the units, in case you're not sure about this or forgot, P is pressure, and we're going to use atmospheres always. Notice over here, I can use any units I want, except you must use Kelvin. So any units for pressure and volume, but Kelvin must be temperature, must be in Kelvin. V has to be in liters when we do PV equals nRT. N is moles. R is 0.0821. And T is temperature in Kelvin. And like we did on the previous slide, we derived R by plugging in standard values for PV and T and N, and we got our R value. So now again, I derive this for you, where you can have condition 1 here and condition 2 here. And so you can compare two different gas samples very easily. So what I'd like you to do is I'd like you to practice these problems, go through and try them, see which equation to use. Let's see if you can do this. Tomorrow in class, we'll discuss how to do these problems. But what I want to talk to you about and finish up with for this video is what do I do when I want to, find some more interesting things out about a gas? Well, I can take PV equals nRT and I can manipulate it. Because I know that the moles is equal to the mass of the sample divided by its gram formula mass, or as we'll use in gases, molar mass. Molar mass is the same as GFM. If you're more comfortable saying GFM, go ahead. So now what I can do is I can rearrange things, and I can say, well, pressure times volume equals mass over molar mass times RT. And if I wanted to, I could rearrange this a whole number of different ways. I could bring the molar mass by itself. I can bring the molar mass by itself, and I can have mass, volume, pressure on the bottom as well, RT like this. Now something else should stick out here for you. The fact that I have mass over volume, that I could just make into density, and that's what I do down here in this next slide. I actually derive density from it. I take this equation here, and we derive density from it. So I have my mass over my volume, and so I can just derive density. I have my molar mass equals mass over volume is density, RT over P. Some people like everything in the numerator, so you could do, molar mass times pressure equals density times R times T. I call it my dirt equation, P equals DRT. So, that might help you. This is my dirt equation. So, just to summarize the types of equations that we have here. So we have our P1, V1, N1, T1 equals P2, V2, N2, T2. We also have our PV equals nRT. We also have our pressure times volume equals mass over gram formula mass or molar mass times R times T. And then we also have our gram formula mass or molar mass times P equals DRT. And so these are, like 5 different equations or 4 different equations. And from these, like these 3 over here are really derived from the same equation. Whereas this one over here, this one could be broken down P times V, P times V, V over T, V over N. You could break it down however you want and you look at the individual laws. So what we're going to do next time is we'll talk about laws and stoichiometry problems. And this we might actually do in class and see how that goes. But I'll also talk about it on the video. We'll do some partial pressure problems and we'll relate that to vapor pressure when we collect gas over water in a lab. And we'll do a problem on that as well. And then we'll talk more. We'll go back to the idea, now that we've seen the math behind this, let's go back to the idea of what kinetic molecular theory actually is, what it says about the gases, how gases move, a quick demonstration on diffusion and effusion, and then what gases do under real conditions, and what molar volume looks like, and what diffusion and effusion looks like, and how different gases move at different temperatures. All right, see you next time. Hope you're having a great long weekend.